Thanks, Pekka. And I'd first like to thank the organizers for inviting me to this wonderful conference. Actually, my first time in Vienna, but hopefully not the last. So I'm going to be talking about the Sobolev homomorphic extensions, basically about my work in the recent years, mainly with Jani Onninen, but today's highlight will be a result on the 3D setting done by myself, Jani, and Standa. But let's go back to the beginning. So where this all started from was this question of Pekka Koskela, who asked in 2018 and asked again on Monday, what conditions do we need from boundary homomorphism for it to extend as a Sobolev homomorphism? So let me give you the planar setting first. So let Y be a Jordan domain in the plane. And let's say P is some exponent between 1 and infinity. So I'm also considering the P is equal to infinity case later. And for me, a phi will be a boundary homomorphism from the unit circle, so the boundary of the unit disk, to the boundary of Y. And this is always, for me, a homeomorphism. So now I'd like to state the main question, which I have aptly named the Sobolev Jordan-Schönflies problem. SJSP for short. And this is basically Pekka's question restated as follows. So suppose phi, this boundary homomorphism, admits a W1P extension to the unit disk. Does phi admit a homeomorphic W1P extension? Exactly. So when you think about Pekka's original question, what are the conditions to find such a phi which admits a W1P homeomorphic extension, of course, one immediate necessary condition is that phi itself is in the trace space of W1P. So on the other hand, if phi is a homeomorphism, the classical Jordan-Schönflies theorem in the plane states that then phi admits a homeomorphic extension. So now we have a Sobolev extension, we have a homeomorphic extension. Can we do both at once? And with Jani and many other authors, we have done many positive and also some negative results on this problem in the plane in past couple of years. But today I would like to kind of focus on the techniques we use to solve this problem. And first of all, if you want to give a negative answer to this problem, if you want to show that some homomorphism does not admit a homomorphic W1P extension, you just need some example. So the technique here is just to cook up some examples. And there are examples where this problem admits a negative answer. So Pekka already mentioned some examples done by his student Yi Zhang. And with Jani, we have more examples which show that the answer to this problem is no in general. So this means that the counterexamples which are given in pairs of domains and boundary mappings phi, they actually exist for all p less than infinity. So Yi gave an example for the case p less than or equal to 2, and we gave some further examples for all p with Jani. But that's only the one half of the story. The other half is, of course, to give a positive answer under some conditions on this domain Y. And how do you show that this problem can have a positive answer? Well, you need some extension technique. So this whole business of considering this problem is about the different extension techniques we can use to construct homeomorphisms that extend a given boundary value, and whether we can find such an extension technique that it also satisfies required Sobolev estimates. But before we get to, let's say, the state of the art, I would like to just go over the basic results we already have in the plane. What are like the basic tools that we can use to extend a boundary mapping as a homeomorphism to address this problem? So let's go through some of the basic planar tools. And the first tool is something also mentioned by Pekka briefly, but I want to put a bit more attention to it. So this is a classical theorem of Radó-Kneser-Choquet. The statement is very simple. So let phi now be a boundary homeomorphism of the unit circle to itself. Then the result is that the harmonic extension H is a homeomorphism itself. So this gives you an analytic means of extending a boundary map as a homeomorphism. You can just take this Poisson integral formula, and it gives you a harmonic extension, which is actually diffeomorphic inside of the unit disk. And it also satisfies some very nice integrability properties in terms of this boundary map phi. So because you have these estimates for the boundary map, or for the harmonic extension in terms of the boundary map, you can actually show the following. So if phi has a W1P extension for p less than infinity, so if phi is in the trace space of W1P, so then H is also in W1P. For p is equal to 2, this is simply the fact that the harmonic extension is actually the minimizer of the energy of the the Dirichlet energy of the 2 norm of the differential. For p less than 2, you don't actually need any condition on this boundary map phi. Every boundary homomorphism of the unit circle to itself is in the trace space of W1P for p less than 2. So that's one of the aspects of what Pekka was talking about on Monday. And this harmonic extension actually works very well even for p bigger than 2. So this gives an affirmative answer to the Sobolev Jordan-Schönflies problem in the case where this target domain is the unit disk. And there's another philosophy here, which I'm not going to write down, but you might want to remember, is that this problem, this Sobolev Jordan-Schönflies problem, is completely invariant under, let's say, bi-Lipschitz change of variables in both the domain side and the target side. Because those changes of variables, if they are bi-Lipschitz, do not change the Sobolev spaces in question. So in this sense, once we have solved this problem for the unit disk case, we have solved it for all bi-Lipschitz equivalent cases as well, which includes, for example, all smooth domains, all Lipschitz domains. So what's left is just some domains with very irregular boundary. And the next tool is, let's say, a bit more suited towards towards general boundaries. So this was a tool used by Hencl and Pratelli in their paper where they were approximating W11 homeomorphisms by diffeomorphisms, and it is known as this shortest curve extension. So the idea here is very simple. Okay, I'm not going to use the disk as the starting domain, but I'm going to use a square S. And now the target domain can be anything. So this is some general Jordan domain. And let me choose here some two boundary values A and B on the square, which are endpoints of such a horizontal segment. I find out where this given boundary map is mapping these two boundary values A and B. And the way I extend my mapping inside of this square is by connecting phi A and phi B by the shortest curve inside of this domain Y. So this written down means that I'm mapping horizontal segments to shortest curves in the target. And you might complain that this doesn't look very injective. I'm looking for homeomorphic extensions, but let's say I take a curve here. It's going to touch this curve here where both of the curves touch the boundary. So this is not immediately injective, but it can be injectified with a small perturbation here in the target side and retaining all the, let's say, estimates you would want from this mapping. So I'm just going to say here that this can be injectified. So Hencl and Pratelli were using this for W11 approximation. And indeed, this has good W11 estimates. In terms of some integrals over the boundary. But actually, it has great Lipschitz estimates. So this is the case p is equal to infinity. And this shortest extension method actually provides you excellent control on the Lipschitz norm inside. And I'd like to state the, let's say, most general planar result in the Lipschitz case here. It was actually originally proved by Kovalev using a different method. But this result, which I'm stating here, can also be shown using this shortest curve extension method with some work. And it goes as follows. So this is giving actually a complete answer to this Sobolev Jordan-Schönflies problem in the Lipschitz case. So let phi now be a Lipschitz embedding of the unit circle into the plane. Then phi actually has a homeomorphic Lipschitz extension. And you can even take this Lipschitz extension to the whole plane. This problem obviously doesn't see on which side of the Jordan curve we lie, so you can get a two-sided extension result even. So the answer to the Sobolev Jordan-Schönflies problem for the case p equals infinity is always yes. And there are a couple other tools you can use. For example, some other tools you can use to solve this case where y is the unit disk. You can use Beurling-Ahlfors extension method. I'd like to talk about that more, but I don't have the time today. You can use some dyadic methods. You can actually construct extensions by hand in at least reasonable cases like the unit disk by splitting the domain and target side in sufficient dyadic sets, and we might see something like that later today. But today I want to highlight these two tools, at least this Radó-Kneser-Choquet and this result of Kovalev's, which can also be shown using the shortest curve method. And let me give you some consequences. But I'd like to preface this by giving you a kind of a fun example of a domain which is a little bit bad. So what if Y is an inner cusp domain? So an inner cusp domain is something that looks like this. And here, I'm not gonna pick yet how sharp this cusp is, but I'd like to give you the following result, which kind of sheds a bit light on what happens for at least domains with a bit more harder geometric restrictions. So here you can see that the inner distance is getting larger and larger. So in this case, there's a curious situation where if p is less than 2, this Sobolev Jordan-Schönflies problem actually has a positive answer for all rectifiable boundaries partial y, and of course this also has rectifiable boundary. And the way you prove this is simply by combining two of the tools we saw today. So you combine this Radó-Kneser-Choquet theorem and this Lipschitz result. You just take any boundary homeomorphism to this rectifiable domain, you pull it back to the unit disk. It's still an arbitrary boundary homeomorphism of the unit disk, so you extend it by Radó-Kneser-Choquet, and then you have Lipschitz extension on top of this rectifiable curve. You can parameterize it by a Lipschitz function, and a Lipschitz function on top of a Sobolev function is still Sobolev. But if p is equal to 2, then the answer for this question is no. So if this cusp is sharp enough, you have some polynomial cusps, then the answer is no. Then there exists some boundary mappings for which you don't have a Sobolev W12 extension, but you do have a W12 extension. And that's precisely because of this loss of a modulus of continuity. But in the case p bigger than 2, the answer is again yes. So for this case, we actually show with Jani that the answer is yes for all piecewise smooth domains y in the target. So this case is drastically different from this p is equal to 2, exactly because these Sobolev homeomorphisms for p equals to 2 satisfy some kind of unique modulus of continuity results that don't hold for general Sobolev mappings or Sobolev functions. Whereas in the case p bigger than 2, you always have a Sobolev embedding. So that's one interesting case which shows that this business is kind of non-trivial. You have weirdly, the only place where it doesn't work is for p equal to 2, but we have a multitude of other, let's say, conditions on domains which give positive results. For example, the following. So with Jani and Pekka Koskela, we showed and Pekka also mentioned this result, that this Sobolev Jordan-Schönflies problem is, let's say, has positive answer for all p less than 2 if this y is a John domain. And in this case, as well as the rectifiable case, let me just, actually, I should have said this already before, that here every boundary homeomorphism actually is in the trace space. Every boundary homeomorphism is going to admit a Sobolev W1P extension for p less than 2. And with Jani, we also looked at more geometric conditions. So we showed that this problem always has a positive answer. For all p if this y is a quasi-disk. For this John domain case, we used pull back by a conformal mapping and sort of dyadic constructions. And for this quasi-disk case, which is more geometric, we had to make an alternative version of some dyadic constructions using this kind of hyperbolic geodesics. But I'm not going to talk about that today. Today I want to focus finally on this 3D case. So now that we know what is the basic planar setting, I want to show what is actually happening in 3D. And let me restate this problem, but now just for the unit ball. So let phi be a boundary homeomorphism of the 2D sphere, so the boundary of the unit ball in 3D. And it's a homeomorphism with phi having a W1P extension does phi admit a homeomorphic W1P extension? So in the plane, this question was rather simple. You could solve it using a variety of tools, for example, this Radó-Kneser-Choquet and this some other methods as well. But why I'm stating it now in just this simple form, where the target is the same domain in the 3D case, is because this is still an open question, actually. So perhaps I'm not erasing this Radó yet. So since it's still an open question, I guess you can already see that Radó is not going to work immediately here. In fact, there are examples by Laugesen which show that this Radó, this basic tool we have in 2D, completely fails in the 3D case. So there is even a diffeomorphic boundary mapping phi of the unit ball to itself such that this harmonic extension is has a Jacobian changing sign. So, okay, I'm just going to write it like that. So it changes sign somewhere in the domain in some sets of positive measure. And, okay, the idea is fairly simple. You just, let's say, look at the sphere itself, split it into the upper and lower hemispheres, and you map them somehow Like you can imagine some kind of tennis ball structure here. And once you do that, you are twisting enough that when you calculate this harmonic extension, which is somehow taking averages, you get some overlap inside. But he showed even a bit stronger result that you can take this, take such an example to be arbitrarily close to the identity mapping in the let's say L infinity norm. So what can we do if these basic tools don't work? I mean, I can assure you that other planar basic tools don't give any better. But we got at least a result of sufficiency. So we have a new extension technique with Standa, myself, and Jani, which shows the following. So let phi from the boundary of the unit sphere again, I mean the unit pole, so the unit sphere, be now a homeomorphic boundary value in. Now this phi itself is in a Sobolev space on the boundary. It's in the Sobolev space W1Q over the boundary. So phi itself has a little bit higher regularity than just being in a trace space, but now this Q is not the same as P. So then phi has a homeomorphic W1P extension for all P which are less than 3/2 times Q. So naturally, if this Q was equal to P, then you could even just take a radial extension. But this result gives that you get extendability in a slightly higher range of exponents. And this 3/2 times Q here is actually sharp in the sense that you cannot put anything bigger here because of the Sobolev embedding result itself. So if you compare the Hölder constants for the boundary map and the extension itself, it shows that you cannot get anything beyond this 3/2 times Q. But there are still questions about sharpness here. So you could reasonably well ask whether we could get this equality here. And then you could, of course, ask the full question here, whether we can actually go to this trace space. So the trace space is a slightly larger space than this W1Q here. But to end this talk, I would like to give you actually a description of this extension method. But it's quite a long paper. It's around 54 pages to describe this extension, because you can imagine describing a homeomorphic extension in 3D by hand is very annoying. But pictures speak more than 1,000 words. And for you today, I have a video or a kind of animation. So an animation probably says even more than that. So let's have the projector on. What do I do here? This here. And maybe the lights should be closed. Okay. So the show is starting soon. Actually, it's starting right now. Let's go and look at this extension. And here you can see that we have two spheres. So here is the domain sphere on the domain side. This is unit sphere. And here is the same sphere on the target side. And we are given some boundary mapping of this domain to the target sphere. And I want to find a homeomorphic extension. So what do I do? First, I'm going to start by cutting this sphere on the domain side dyadically into sets. So let's start by drawing here some dyadic decomposition of this domain side here, like this. And as you can see, there are also some cuts on the target side, and these are the images of each dyadic set under this given boundary mapping phi. So we get then topologically a dyadic decomposition of the target side, and now this is going to help us with constructing such a homeomorphic extension inside of this sphere. And these extension problems themselves are actually very local questions. So it's going to be enough for us to describe how to extend this boundary mapping in a small neighborhood of, let's say, one dyadic set, one dyadic square on every small level. So let me go somehow just looking at one of these dyadic squares, and because we are on a very small scale, I'm gonna be able to flatten everything out. So let's flatten this out, flatten it out here on let's say the lower half space. And I'm gonna, let's say, improve the picture a bit because it looks a bit silly now. So here I have again this dyadic square. You can already see the next level of dyadic squares in the domain side. And what I've actually done on the target side is I've taken a piecewise linear approximation of these target curves, which is going to help when we actually construct this extension by hand. But now we are actually going to this part where we need to start constructing the extension. So where we are doing this. So let's imagine now that this part here on the, let's say, lower half space, or not the lower half space, like the plane, is the boundary, and everything in the upper half space is my domain, and everything on the upper half space in the target is my target domain. So I need to somehow construct my extension in this space above this 2D shape here. So what am I going to do? First, I'm going to lift here one copy of this dyadic set, and I'm going to do the same thing of the image set. So of this image curve of one dyadic level, and I'm going to do the same on the children, but I'm going to only lift it to half of the level. So here the height is 2 to the minus n and 2 to the minus n plus 1. And now, related to what I was talking before, that this is actually a piecewise linear approximation, I'm going to have to get a little bit sharper approximation on each dyadic level. So I'm actually going to have to change this boundary curve in the target side a little bit. Okay, I'm going to change it to another curve there. So when I make the approximation better, the curve might change. But now I'm going to need to define this mapping between these two, let's say, planar regions. So I'm going to simply, on the domain side, connect these two squares into this kind of box. And on the target side, I will find some way to create this sort of cylindrical region between the original curve and the curve with a little bit better approximation. So I'm going to define some sort of homotopy between these two curves. And that is going to define this sort of cylindrical shape. Now I have honest 3D shapes on the domain side and the target side, and I need to somehow define a way to extend or to define a mapping which sends this box here to this cylindrical region here. So let's look at these two boxes a little bit closer here. So on each box, I need to define my mapping inside of the box. And I'm going to actually define it on every horizontal level individually. So when I look here at the horizontal levels on the domain side, they are going to be mapped to exactly the same horizontal level in the target. So for each level, I will have some Jordan domain on the target side, and I just need to find a way to define this mapping as a planar homeomorphism between this red square and this target domain here. So let's look at these planar regions a little bit closer themselves. And what I do on each planar region is actually going to be using the shortest curve extension method. So here, I go through this square on the domain side with these horizontal lines, and I look for each green line here, what is the shortest curve between the corresponding boundary points. And this is going to give me an extension, which is defined on this red region. That's going to define an extension on this whole whole box. That's going to define an extension for every dyadic box. And when we consider every single dyadic set on the boundary, this is going to give me a tiling of the space, which is going to give a homeomorphism of the sphere to itself. Of course, I'm brushing all the dirty details under the rug. I'm not telling you how we are actually getting Sobolev estimates, but the key point is that this shortest curve extension is giving you nice Lipschitz estimates, and I'm getting some nice Lipschitz estimates in each box. And when I sum these up, these Lipschitz estimates, when I look at what these Lipschitz estimates mean for the Sobolev norm, when I estimate each Sobolev norm individually in each box, I'm going to actually get some nice control in terms of what is happening on the boundary. But of course, there's still a lot more details that are not missing here. For example, I need a lot of nice control of this shortest curve extension in terms of, let's say, the time variable. But I'll leave that for another time. So thank you very much. That's all I had to say.